I want to thank John Eckstein for inviting me and the other members of the organizing committee. It's a pleasure to be here. It was really rough getting here from Manhattan, but I had a party last night, so it was just hard getting up this morning, not coming here. I'm today going to talk about ADMM for multi-affine constrained optimization. And actually, when I was invited by John, I asked him to invite Wenbo Gao to come and give a talk, because he's the person who really deserves most of the credit for this. By most, I mean a number very close to one. And he is sitting here, so if you have any questions that are difficult, I would appreciate if you ask him. Okay, but the easy ones you can ask me. It's okay. It's easy to talk about ADMM here, since everyone knows what ADMM is. And of course, the classical method was really described and developed for handling f of x plus g of y, where x and y have been connected by some linear equations. And there is the method, which I don't have to spend any time on. But the point was, whether you did variable splitting to get, you originally had a function of f plus a function of g of x, and then you split it into x and y. The main thing was that it was with linear equations. And everyone knows the history of this from this audience, goes back to really Gabay and Mercier and Glowinski in the 70s. But it truly goes back to Douglas and Ratchford and Peaceman-Ratchford in the 50s, so it's more than 65 years old, I guess. So it's been around a long time. And I remember reading the paper by Léon Mercier, which did a very nice analysis of Douglas Ratchford. And I remember that this quote, which I've never forgotten, in which he said, well, it's very easy to, these nice results about two blocks of variables. But the quote was something, it seems rather difficult to prove anything about three blocks. And, Léon's is, a Fields medalist. And when someone like that says it's rather difficult, it means he tried very hard and he couldn't. And so I thought that was an understatement. And of course, since that time, people have figured out how to modify. I mean, straightforwardly, it doesn't work with three blocks, but, you can handle many more blocks, and there are various things. Wotow and his student Damek Davies proved things about variations of what you can do with a third block to make sure that you get convergence. In any case, another thing that's interesting is when Boyd, Parikh, Chu, Palieto, and Eckstein wrote this survey a few years back. ADMM has become so important that I looked it up, and in last year, in 2017, that paper has 1,875 citations on Google Scholar, which is kind of amazing. I'm sure John knows very well that when he wrote his paper with Bertsikas, he had 20, 30, 40, whatever citations, not 2,000. So huge increase in interest in ADMM. And I think in recent times, there's been major work in extending it for handling non-convex objectives. And I particularly like the paper by Wotow, Wang, and Zheng. There's also papers by Tom Luo and others. Some people are here who have been able to extend ADMM in basic ways. But until, I think, the present time, and this work with Wenbo and also with Frank Curtis, but mainly Wenbo, all the results are really referred to the main, fully theoretical results are for when the variables are constrained by linear equations. I mean, you can always have like non-negativity, or where you have a set X and you project onto it, but then you have an indicator function that projects on a set. But usually the theoretical results all depend upon linear constraints among the variables. So we're going to talk here about multi-affine constraints. And a multi-affine function is a function which, when you let all the variables, fix all but one block of variables to be, set them all to be fixed, the function is linear. That's what multi-affine means, okay? And multilinear means the same thing but without the constant term. And in particular, the kind of problems that arise very frequently are bi-affine problems, where essentially you have, x times y type terms in the objective or in your problem. And they're quite prevalent. So I think extending things to multi-affine maps is important. Just the simplest, this is a simple multi-affine function. They are highly non-convex. So here is just you're minimizing a quadratic around the point A11, and you have, if you look at that constraint, you can see that xy is equal to is z1, and x is what is it? Is z2 and y is z3. So you have a constraint that essentially says that z1 is equal to z2, z3. So you're minimizing just this a ball function around the point A11, subject to this very simple bilinear equation. And if you have, if you pick A bigger than 3, you actually have 3 different kinds of constrained stationary points. They all have the form rj squared, rj, rj, and it turns out if the point is r3, there's a global minimizer at this point. There's a spurious local minimizer at this point, and there's a saddle point at this point. So you have in general, this is a rather nonlinear function, even though it's very simple. Okay? So what we're going to talk about is, in much more general terms, we're going to have a function, a whole bunch of blocks of variables, but the function can be written as some general function f of these variables. And we're going to have different kinds of sets of variables. The z variables are going to be treated a little differently than the x variables. You have a function of z0, a function of zs, a function of the block z2. And then you have the constraints, which are these multi-affine constraints. You have a multi-affine function of the, either you have variables like this, a multi-affine function of the x's and z0, and then a linear function of z1 equals 0, or you have a multi-affine function without the z0 and a linear function of z2, okay? And the theory that's in our paper, handles basically this generality, okay? Under, of course, certain assumptions. And those assumptions are, so for those of you who have read Wotow's paper, Wang, Yin, and Zheng, a lot of the underlying assumptions, et cetera, really extend what he has in his paper, so some of these things will look familiar, okay? Because you have this non-convexity and you need assumptions to make things work, right? We're going to always update the variables in the order that we'll update the variables, the x variables first, and then the z variables. We need that the image of the q's, the linear terms, that their images include the images of the affine terms, the multi-affine terms. We need that the objective function is coercive in general, the whole function. We need, those, in order for theory to go through, if we have that h function of I forget what it was, HH is a function of Z0. That has to be convex and lower semi-continuous. G1 has to be strongly convex. That's the one of ZS. G2 has to be just Lipschitz differentiable. It doesn't have to be convex. Okay? And for large enough rho, we make the assumption that every ADMM subproblem attains optimality. Okay? Those are the basic assumptions, and a lot of what we can prove about this multi-affine ADMM requires only the assumptions 1. And with those assumptions, you can prove essentially that the augmented Lagrangian, which acts as your Lyapunov function, that converges for a given set of z's. Okay? And then the second set of assumptions are, as you see here, that the first part of the objective function has to be Lipschitz differentiable, especially if it's broken down into a sum of functions over each of the blocks of variables, and it's continuous on its domain, and each of those functions has to either be convex or Lipschitz differentiable. They don't have to all be convex, okay? They can be non-convex. But for instance, if you have a non-smooth function, you need the convexity. This second set of constraints, this second set of assumptions, which I don't think it's worth going into detail about these, but these are technical things that you need to prove convergence. So the algorithm looks like this. It's your standard thing, but we, as I said, we will do the x variables first and do their augmented Lagrangians and do those minimization problems. Then we do the z variables, and then we update the matrix of Lagrange multipliers. Okay? And here I'm just writing this down as the full set of constraints. You may have different sets of constraints, but and the W maybe breaks down into individual subblocks, but we're just writing it in its simplest way. How many slides am I at? It doesn't show. Okay, so the main results, theoretical, are that under assumption 1, this algorithm has limits points, and every one are constrained stationary points with respect to Z0, Z1, and Z2. If you have the second set of assumptions hold, then every limit point of the algorithm is a constrained stationary point of the original problem. Okay, so that's the full convergence result. And I don't know if it's worth, that's the formal statement of it, okay? But it's exactly what I said, under sufficient, assumption 1, under sufficiently large, penalty parameter in the augmented Lagrangian, the sequence produced is bounded, and every limit point satisfies the multi-affine constraints. And there exists a sequence of essentially subgradients such that the subgradients go to 0, and this is a 0 of this function, and with this is the adjoint, the C transpose of this linear map, and Z star is a constrained stationary point of this problem. Okay, so in other words, for Z star, you get a solution of this problem. Okay. Wait. Okay. But the full theorem says that under assumptions 1 and 2, for the sufficiently large rho, you get a sequence that converges every limit point in both the x and z's is a constrained stationary point of the original problem. Okay? Okay, and that's the reference on arXiv. Okay, so here's some much more accessible slides. Examples of problems that are of the form that the theory applies to. Perhaps the simplest is non-negative matrix factorization. You want to find a matrix B that can be written as a product of two non-negative matrices. Non-negative means, the elements are non-negative. And so you want to find that b, which in 2 norm is, and of course that should be a Frobenius 2 norm. It's the sums of squares of the elements of b are the difference from the, of the difference between the element of b and the element of xy, okay, over all elements I and j. And the way you can write that is we'll use a indicator function for the non-negative orthant. So we will find the minimum or the infimum over z, x, and y such of the indicator function on the non-negative orthant for x, and the same thing for y, plus 1/2 z minus b squared, subject to z equal xy. So you have here the multi-affine constraint. So you have in this case, you have a nice set of convex functions, although not smooth in the case of the indicator functions, but you have convex functions, sum of 3 convex functions subject to a multi-affine constraint. Now, maybe even before I go on, the reason that all this should work, and it should make sense, and I think Katja sort of alluded to this, is when you have multi-affine constraints and you write down the augmented Lagrangian, has the constraints. You have you have your Lagrange multiplier times the multi-affine function, and then you have a rho times the multi-affine function squared, right? When you then solve a subproblem and you fix your variables, the variables that are fixed at that particular subproblem, you're fixing, let's say, in this problem, you're fixing, let's say, the y. But then it's linear in x, so it looks in the multi-affine case, the subproblems that you see when you're solving your sequence of augmented Lagrangian subproblems look exactly as if you were dealing with linear constraints. So you would think, gee, it should work. It seems like it's very much like the standard method, except the theory doesn't go through so simply. I mean, I forget how many theorems and lemmas there are in this paper, but I think it's well over 30. There's a lot of work to prove that your intuition works. Okay? And there are certain things that you need to have in the proofs. But the point is that that's why, and it doesn't matter whether it's biaffine or multiaffine, because if it's multiaffine, it's x, y, z, w, whatever. You fix everything except x. It's just linear in x. So in the augmented Lagrangian, it's as if you had a linear equation. And so it looks exactly like ADMM, classical ADMM. Okay. So, but in order for things to work, if you look at this problem, if you go back to this problem and you minimize respect to x and minimize respect to y, you don't get simple subproblems. And the whole idea, of course, of ADMM is to do splitting or do whatever you can so that the subproblems that you encounter when you're doing your steps of doing the subproblems, each subproblem has a closed form solution, or is so simple that 1 or 2 iterations you'll get the answer, right? So that things become easy. So in this particular problem, that if you think about that, you'll see that it's not so simple. You won't have subproblems that are closed form. However, if you split x and y, and you let x equal x prime and y equal y prime, now when you minimize respect to x prime, you get a quadratic with an identity there, and so that becomes a trivial problem. Same thing with the y prime, and when you do it with respect to z, you just get a simple quadratic. But the point is, you end up with and when you do it with respect to x, you get or y, you get quadratics. So everything is got closed form solutions. Okay, in the subproblems. It turns out, and these subproblems are always convex quadratics, as it says here. And when you do the x prime and y prime, because you end up with a quadratic because of the augmented Lagrangian there, but you're minimizing over the non-negative orthant, so it's the closest point, you in that quadratic, it's something minus a point A, so it's the closest point A to the non-negative orthant. Well, that just means you knock out all the variables that are negative and make them 0. That's the closest point. So it's a trivial amount of work to solve those subproblems. It turns out, though, that in this version of this problem, it actually doesn't satisfy all the assumptions that we need for convergence. And what you need to do is you actually need to define some slack variables. So for the x equal x prime constraint, you need to write that as x minus x prime equal x double prime. Okay? And you need this to do the same thing with the y primes. John, you're looking unhappy. Yeah, it's sad. So you end up doing that. And of course, you have to penalize them. And so as you let mu go to infinity, you make it very large, of course, you're getting x equal x prime, and everything goes through. And it turns out you can let mu be very, very large. It's not like penalizing the original constraint. Your constraints, the theory tells you that you're going to get z equal xy. Okay, of course, xy is not going to necessarily be x prime unless x double prime is 0, that sort of thing. And it turns out the extra work involved in introducing those extra blocks of variables is trivial. Because if you look at the problems in x double prime, you just get a simple quadratic with an identity or scaled identity as a Hessian. So it's a matter of just setting. You have an n vector, and you just set the x double prime to the n vector. I mean, it's pretty trivial in terms of computation. Okay, here's another problem: sparse representation learning. This includes dictionary learning, inexact dictionary learning, where you want to find the dictionary. You want to write. You have a data set B, which you want to express it as some sparse combination of atoms. Those atoms are the atoms in a dictionary X, and Y is how you combine them to get represent the data B. And so, and one version of the dictionary learning problem, you want the atoms all to have norm 1, stating Euclidean norm 1, so you want the columns of X to have Euclidean norm 1. So your problem can be written out this way. Over the indicator set of columns of a matrix that have norm 1 plus the 1 norm of Y, because you want to have a sparse representation of the data elements B in terms of the dictionary X. And you want to choose X and Y so it's as close to B as you can, right? And of course, you can write it this way. You just Z minus B, you let Z equal X minus equal XY. So now you have a multi-affine constrained, in this case, convex problem. And if you add these slacks, that is completely satisfies the theory of that's in our paper. And we've run problems. I mean, Wenbo, I don't have any results here, but you run big dictionary learning problems, and it works pretty well. There are specialized algorithms that actually, there's an algorithm called IPALM that works extremely well, and it's hard to beat, but we can usually do as well as those methods. But the advantage of ADMM, you can add other constraints. There are a lot of methods for doing problems, let's say, like dictionary learning, but they're very specialized to exactly that formulation. When you start adding other constraints, the methods completely do not work. They're not designed for it. Whereas ADMM, you can always add other linear equations, for example, and it doesn't, you can add other terms, and they're related to the other variables, the blocks, in terms of linear equations, and everything still goes through. So it has great flexibility. Here's the problem that Katja was talking about, the risk parity problem, where you just the simplest problem she was talking about is just you want to find a feasible solution of this set of quadratics and upper and lower bounds and a linear equation and the weights of the portfolio. And if you define this matrix and you write the Hadamard product as with a, x dot 0, I being xi, yi, then you can write that problem in this form. Okay, it's a indicator function over a box, which again turns out to be easy to when you do your optimization, your subproblem. It's trivial. We're adding these slack variables, and this is what it looks like. Okay. And again, everything I'm showing you has got closed form solutions for the subproblems. So this is actually the problem that actually got me motivated to do this whole thing. Was training neural networks. There's a paper by I remember the last author, Goldstein, who did. He was a student of Stan Osher, and I wrote these papers on Bregman iteration. This is how Wotow and I got started, trying to do denoising, and we didn't call it ADMM. We always called it ADAL, augmented, alternating direction augmented Lagrangian method, and. Tom Goldstein was subsequent years later a graduate student of Stan Osher, and he came out with a paper that's called Split Bregman. Because actually when we did this, I actually proved that this Bregman iteration converged. I didn't realize that I was doing augmented Lagrangians when I did the proof. It was just a method of augmented, not ADAL, not ADMM. It was just straight augmented Lagrangians. And split Bregman is nothing more than ADMM. But it has more citations than ADMM. The community that got to know Bregman iteration, et cetera, which is augmented Lagrangian, is a very big a group of people doing denoising and things of that sort, and compressed sensing. And then split Bregman is nothing more than ADMM, pretty much in that case. It can be generalized where it's not ADMM, but whatever. And so he has a paper with a bunch of computer scientists for solving deep neural networks using essentially split Bregman, not ADMM, and does not have a single theorem in it. Nothing's proved, okay? But what they did was they took these really, deep neural networks usually means they have at least one inner layer you can't see. So they're not very deep. They're shallow, deep neural networks, okay? When people say deep neural networks, a lot of them that actually people use have one layer, okay? Some of them might have 100 layers, but very often one, sometimes 3. But whatever. So at each layer, what happens, how neural net, I don't think I have any pictures. I don't have any pictures. But neural networks are, layers, nodes, and then all the standard feed-forward neural network is all the outputs from the nodes that, get transmitted to all the next layer of nodes. First, they're hit by a activation function, which is something like ReLU, which says that if the value of the signal is less than 0, set it to 0, and if it's greater than 0, set it to what it is. So it's a function which is 0x, okay? And there are other ones. There's a sigmoidal, which goes 0x 1. Then there are, of course, continuous versions of it, which is the hyperbolic tangent, okay? But they're fairly simple functions. And then after you have this function at every point in the network on a layer. So it's just a bunch of, it's just these values that are coming out, and they're vectors, and sometimes they're and they're actually usually matrices. of data because you have, for each data point, like each image that you're feeding to the neural network to train it means optimize. To train it, you have one set of signals coming out. If you have lots of images you're training under, like 100,000, then you have 100,000 images coming out, 100,000 things coming out. And so the thing comes out, it's hit by this nonlinear function, very simple nonlinear function, and then a matrix takes it and takes every point here and distributes it to every point here. So if you have n points here and you have m points here, it's a m by n matrix that just takes the n vector here and converts it to an m vector. And of course, if you have a whole bunch of n vectors, I mean, because you have lots of data, it's a matrix of those things. Okay? So that's all it is. And so their idea was just take the, so there's the ReLU there, but here, the matrix here that takes the active outputs at layer L minus 1, it hits it. So, okay. The output coming to a layer L is called ZL, okay? It's hit with an activation H. H is like this ReLU function. It now becomes an activated output. That activated output is then transformed to the next input, to the next layer, by hitting it with a matrix, okay? Now, you look at this. What is this? Okay, this is nonlinear, but this is biaffine, okay? And so instead of doing what everyone typically does in solving deep neural networks, or undeep neural networks, or in any kind of machine learning, is they use, because as you do this from layer to layer, you're writing a function of a function of a function of a function of a function, and eventually you get to the top layer, and there you actually has your least squares or your logistic least squares or some sort of function which says how well you did in fitting the known data. And the variables are the elements of the matrix X. And I mean, there could be a slope here or something, but it's really the elements of the matrix X that you don't know. And then there's some at the top layer, you may have some fitting function, you have some other variables that you need to fit, okay? But you're just doing a kind of nonlinear least squares of some sort to do fitting. So that's why it comes out to be optimization. But you're doing nonlinear, you're doing nonlinear optimization. You're doing least squares, you're doing data fitting, right? And you're trying to figure out what parameters in the model will give you the best fit. And then you, of course, use that to actually test real data. Okay, so the error function is at the top layer. The error function could be just straight least squares, for example, or logistic least squares. And there might be a regularization term, because you want sparse solutions. So that might be the sum of, the one norms of those variables, right? And then this just says what goes on from layer to layer. And you start at layer 0, and that's just your input data. That's just like you have all these images, and you have the pixel value for every one of those images on the, let's say, 10,000 pixels in an image. And then you have another 100,000 images that you're using. So these are very big problems. But what this does, instead of doing forward differentiation and then backward differentiation, which in machine learning is called forward and back propagation, but it's nothing more than automatic differentiation, right? It's the chain rule. Who was Chain? I don't know. Frederick Chain. Chat. Maybe he was French. I don't know. The chain rule. Yes, it's a chain rule. And there's now software for doing all this. And it's done very efficiently. If it's been programmed up there's software to do this that's done very efficiently. And of course, if you're doing just stochastic gradient descent, it really is nothing more than differentiation, chain rule. So here it is. You're minimizing this, and you have all these equations. Okay, these are all bioaffine equations. These are a little more, not bioaffine, but those are your problems. Anyway, you can now write this in the form of a bioaffine model that will fit our theory for doing multi-affine ADMM. You have these multi-affine equations, the bioaffine in this case. We put this into the objective. And because of things like ReLU, they're so simple, when you actually solve it, it's trivial. So again, all the subproblems here can be solved trivially. They all have closed form. So it's not trivial. You have big matrix. You have big quadratic systems of equations to solve, but they all have closed form solutions. Okay? Now, I don't have any results because if you really want to test this, you want to do it on really huge problems, and we haven't written anything to do that. But I can tell you that this paper by Goldstein and his co-authors, again, don't look Goldstein, look at ... Goldstein. They have good results doing on, multiprocessors, doing this decomposition. And they don't really do ADMM. They only throw the top layer into the augmented Lagrangian type, split Bregman. It's a hodgepodge of heuristic versions of ADMM, okay? But this was the initial motivation of looking at this. Here's another, what time do I have? None? Okay. Well, let me just show you one. This is convolutional learning, but let me show you one other thing. So this is just like dictionary learning, but it's for deconvolution, and there's some nice results given by Wenbo. Another thing that turns out to be a hot topic these days is non-convex formulations of convex problems, right? So you take a convex problem. Can I have 2 minutes to do this? Convex problems like, non-convex problems like RPCA, robust principal component analysis. You want to take, let's say, video image. You want to make it foreground, background. Actually, you want something that's low rank and sparse, or sparse and anyway, you want sparsity. So you want to minimize the rank, some rank plus some lambda times the zero norm. In other words, the cardinality of something. Oh, so what do? You replace the cardinality by the one norm, and you replace the rank by the sum of the singular values, the nuclear norm. So now you have a nice convex problem. And of course, the theory that came about for compressed sensing and then RPCA, my colleague John Wright at Columbia, with Candace, in very high probability with right assumptions, you're solving your convex problem, your non-convex problem by this convex relaxation, you get the same answer. Okay? Now what you do is you take this nice convex relaxation and you make it non-convex again. So you start with non-convex, make it convex, now you take it non-convex. So how do you take it non-convex? Instead of working with minimizing the rank of the matrix, write the matrix Z, write it as UV transpose. And if you think that the rank will be never greater than 27, make U have 27 columns and V have 27 columns. Now you've imposed a rank constraint on your problem, solve that problem, but now the problem is much easier because doing a full SVD or even a partial SVD is very time consuming. Okay? So again, what do you end up with is a multi-affine problem. Okay? So it's useful in that, and it works very well. And I could show you a video of this escalator problem, which everyone has seen, but we actually did a little version of it that actually, how do I get rid of this? How do I get there? So I'm sure you've never seen the escalator with actually, we separated it into the, that's the video, that's the foreground, that's the background over there, that's the foreground, the people walking through it, and that's the escalator. So we actually did an extra decomposition, but doing it with multi-affine ADMM. But anyway, it's just a picture. It's a video. Thank you.